And when we come to ethylene, this is the conformational isomer. Welcome all. Today we will discuss conformational isomers. It's conformations of ethane, butane like molecules. Okay. So what is conformation? What is conformational isomers? We know that conformational isomers are due to or which arises due to free rotation along carbon-carbon single bond. Okay. So we know that for each minute rotation there will be a conformational isomer. Okay, so infinite conformational isomers are possible for a molecule. The question arises, which conformation will have maximum energy? Which conformation have minimum energy? Why we are bothering about energy? When energy is maximum, the stability will be minimum. So, like that, we want to study the energy of different conformational isomers in order to understand more about its stability and property. And the study of energies of different conformations in order to understand the properties and stability of conformational isomers are called conformational analysis. So, we are going to discuss conformational analysis of some molecules. So, let us take an ethane molecule. Here, we can see that the different conformations, that is eclipsed, staggered, different conformations are there during a rotation from 0 to 360 degree. Okay, so what is this degree? Here we are given a degree of rotation. That degree of rotation, that is, or we can say that the angle between the hydrogen atom of adjacent carbon atom. So when we take this ethane molecule, here we can see that the two hydrogen of this adjacent carbon atom are eclipsed to each other. And the angle between these two, that is dihedral angle. The angle between the hydrogen atom of adjacent carbon atoms are called dihedral angle. Dihedral angle. So here in the ethane molecule, in the case of eclipsed, we can see that the dihedral angle theta is equal to 0 degree. In the next case, here it is theta is equal to 60 degree. So when it becomes 60 degree, it turns to a staggered conformation. It turns to a staggered conformation. So what is the difference between that eclipsed and staggered conformation? What's the difference? In the case of eclipsed, the bonded electron pairs of adjacent atoms are close to each other. In the case of eclipse, the bonded electron pairs of adjacent carbon atoms are close to each other. And as the bonded electron pairs are close, they experience a repulsive force. And this repulsive interaction is known as torsional strain. It's known as torsional strain. So, for an eclipsed conformation, torsional strain is maximum. In the case of eclipsed, the torsional strain is maximum. So, we can see that eclipsed will be having high energy, that is, we can see that 3 kilocalories per mole. When we convert to joule, it will be approximately 12.6 kilojoules per mole. Okay, so when we rotate it into 60 degree, what happens? The angle becomes, the hydrogen bonded electron pairs will be as far as apart. So the repulsion will be minimum. So in the case of staggered, the repulsion is minimum because the distance between them is less. That's why the energy is less for staggered. Again, when it rotates 120 degree, we can see that it is eclipsed. So the energy is maximum. Then again it is rotated to 60, that is 180 degree. We will be getting a minimum energy staggered conformation. Then with 240 eclipsed, 300 staggered, then when come to 360 eclipse conformation. So when the torsional strain is maximum, it will be having high energy, and we know that universal law, maximum energy, minimum stability. So the least stable form is eclipse conformation, and more stable conformation is staggered conformation. And the energy difference between the eclipsed and staggered is 3 kilocalories per mole. So this is the conformational analysis of ethane molecule. And we can come to the existence of this conformational isomers when they are in equilibrium. When they are in equilibrium, staggered will be predominating, because this having minimum energy. As they have less torsional strain, they will be possessing minimum energy. So staggered is the predominating form in conformation among the conformational isomers of ethane. So let us take another molecule, that is butane. Butane can be considered as a disubstituted ethane molecule. In ethane molecule, instead of one hydrogen, there is a CH3. Instead of hydrogen, there is a CH3. So coming to conformational analysis of butane molecule, apart from this dihedral angle and torsional strain, we should come across another term, that is steric strain. See, we can plot the dihedral angle and the potential energy of ethane. Here we can see that the butane molecule in the first case here, it is an eclipse conformation. Here the dihedral angle theta is equal to 0. In the case, the dihedral angle theta is equal to, for the eclipse conformation, theta is equal to 0 degree. Here, what the torsional strain is, the interaction, or it is the repulsive interaction between the bonded electron pair. What is the steric strain? Due to this CH3 group, these two groups are bulky groups, and there will be interaction between them. Why? Because the distance between these two groups will be less than that of van der Waals radii. When the distance is less than van der Waals radii, there will be repulsion between the substituted molecules, and that gives steric strain to the molecule. That steric strain imparts higher energy. So in the case of eclipse conformation, torsional strain will be maximum because the bonded electron pairs of adjacent atoms are close to each other. And when we come to steric strain, the two methyl groups are close to each other, so there will be maximum steric strain. So when we come to this molecule, when it rotates to 60 degree, what happens? The torsional strain will be decreased, and also the steric strain will be less. Steric strain will be relatively less. Okay, that's why the energy, we can see that the energy is coming low. That is 0.88 kilocalories per mole. The first case, we know that it is 5 kilocalories per mole. Okay, so in the next rotation, it will be getting eclipse conformation. But it is not fully eclipsed. So when the dihedral angle is 120 degree, it is partially eclipsed. This 0 degree is fully eclipsed conformation. This is fully eclipsed conformation. And whereas this conformation, this is an eclipsed conformation, but we call it as partially eclipsed. That is theta is equal to 180 degree dihedral angle. Then when we come to 180 degree, what's the peculiarity of this conformation? That is CH3 is as far as possible. That means steric strain is minimum. Steric strain is minimum and it is a staggered conformation. Staggered conformation, or we call this as anti-periplanar. Anti-periplanar means these two groups are opposite to each other. They are anti-periplanar, whereas this eclipse is called syn-periplanar, because syn means they are on the same side. This is on the opposite side. They are as far as possible. So it is anti-conformation or anti-periplanar conformation or staggered conformation. Here steric strain is minimum and torsional strain is minimum. So it will be having minimum energy. Minimum energy. Then next, when we rotate 240 degree, again it will be coming to an eclipse conformation, but it is partially eclipsed. It is a partially eclipsed conformation, and another 60 degree, that is 300 degrees we will be getting some more apart conformation, that we call it as Gaussian conformation. So we will be having two Gaussian forms. That is, when theta is equal to 60 degree and theta is equal to 300 degree, we will be getting two Gaussian forms. And when it is come to 360 degree, again we will be getting what? Eclipse conformation. We call it as syn-periplanar. So when the dihedral angle changes from 0 to 360 degree, we will be getting eclipsed, that is fully eclipsed. We call it as syn-periplanar. Okay, then next one is partially staggered. We call it as Gaussian conformation. Then it is partially eclipsed. Then we will be getting anti-periplanar or completely staggered, or we call simply called anti-conformation. Anti-periplanar, then partially eclipsed, then Gaussian, then we will be getting syn, that is eclipse conformation. Okay, and other conformation in between these all conformations, we call it as skew conformations. So going through this energy difference, we can say that the conformation which are most stable at equilibrium is anti-periplanar or anti-conformation. And the least stable is syn-periplanar, or it is eclipsed conformation. Okay, so this is the conformational analysis of butane molecule. Here there will be contributing torsional strain and steric strain. These two factors decides the stability of different conformational isomers. So eclipsed, fully eclipsed are known as syn-periplanar, and fully staggered is known as, that is, steric strain is minimum, torsional strain is minimum, which we call it as anti-periplanar. Okay. So let us take another disubstituted ethane, that is ethylene dichloride. In the case of ethylene dichloride, the main conformations possible, that is difference between energy can be considered for these three conformations. This we know that it is an eclipsed, fully eclipsed conformation. This is a Gaussian form. This is an eclipse conformation. This is the Gaussian form. And this is the staggered or anti form. antiform. Here we can see that in this case dihedral angle is 0, and what happens? The torsional strain will be maximum, steric strain will be maximum. Apart from that, here we can see that the chlorine will be imparting a dipole moment. Okay, so there will be a dipole-dipole interaction that will be maximum here, and the stability in this case can be also explained by dipole interaction. Dipole interaction. So this will be having higher energy when we compare to butane, eclipsed form of butane, because apart from steric and torsional strain, there will be dipole-dipole interaction between these two chlorine atoms. And when we come to this, the dihedral angle is 60. So this chlorine atom is somewhat away from each other. So the steric strain will be less, torsional strain will be less, and the dipole interaction will also be comparatively less. And when we come to staggered, we can see that the dipole interaction will be least in this case. So steric strain and dipole interaction will be less. So in this case, the staggered is more stable due to less torsional strain, less steric strain, and less dipole interaction. Okay. Another example for substituted ethane is ethylene glycol. Ethylene glycol. See, this is an eclipsed conformation where the two OH are very close to each other, that I have already told. That is, in this case, that is in this eclipse conformation, the distance between the two OH or two hydrogen of adjacent carbon will be less than the van der Waals radii. And here it is Gaussian conformation. In this case, the OH are somewhat distance from each other. And in this case, they are as far as possible. Here, which is more stable? When we compare the steric strain, torsional strain, this will be having high and this will be having least. Apart from these factors, hydrogen bonding contributes stability here. In this case, hydrogen bonding is possible in between this oxygen and hydrogen, and that stabilizes this type of molecule. The same case is there in the case of ethyl chlorohydrin. In the case of chlorohydrin also, in the Gaussian form, there is hydrogen bonding between the chlorine and hydrogen. So, normally in all cases, in the case of butane, ethylene dichloride, we had seen that the antiform, that is staggered form, is more stable. But in such cases where they are stabilized by hydrogen bonding, Gaussian conformations are more stable. Gaussian conformations are more stable when we compare to the antiform. And we know that the least energy is for the least stability is for the eclipsed, that is high energy due to steric strain, torsional strain, everything will be therefore eclipsed. Then among these two, which are stable, Gaussian is stable because intramolecular hydrogen bond will be stabilizing. Here they will be stabilized with energy 20 to 29 kilojoules per mole. The stabilization of Gaussian form in this case. Whereas in the case of ethylene dichloride, the stabilization is 18.83 kilojoules per mole. Okay, so in the case of conformational analysis of molecules, conformations, we go through four terms, that is torsional strain, steric strain, dipole movement, and here the last one is hydrogen bonding. So hydrogen bonding is more pronounced in the case of ethylene glycol and ethylene cyanohydrin. Okay, so this about the conformational analysis of ethane molecule and substituted ethane. We had considered butane as substituted ethane molecule. In the case of ethane molecule, we go through the torsional strain. We explain the energy difference, the stability of molecule by using torsional strain. In the case of butane molecule, both torsional and steric strain are involved. And when we come to ethylene dichloride, dipole moment is another factor which stabilizes the conformational isomers. When we come to ethylene glycol and chlorohydrins, hydrogen bonding will be more pronounced, and in such cases, Gaussian conformations will be more stable than anti or staggered conformations. Okay, thank you.